Have you ever considered how devices like old-fashioned radios could precisely pick out just one signal from countless others, or how certain filters achieve incredible selectivity? This remarkable ability stems from a specific electrical phenomenon known as resonance, a truly fascinating concept in alternating current circuits. Resonance in a parallel RLC circuit happens when the inductive reactance of the inductor becomes exactly equal in magnitude to the capacitive reactance of the capacitor. This crucial balance occurs at a specific frequency, which engineers call the resonant frequency, resulting in a unique electrical state for the circuit. The core reason this balance is so significant lies in the nature of alternating currents through inductors and capacitors. In a parallel circuit, both components experience the same voltage. However, the current through the inductor lags this voltage by 90 degrees, while the current through the capacitor leads the voltage by 90 degrees. When their reactances are equal, the magnitudes of these two currents become identical, but they are exactly 180 degrees out of phase with each other. This perfect opposition means they effectively cancel each other out in the main supply line. Consequently, the power source only needs to supply current to the resistive part of the circuit, leading to the highest possible impedance from the source's perspective and the lowest total current drawn from it. To achieve or predict resonance, you typically adjust either the inductance, the capacitance, or the frequency of the alternating current source. The resonant frequency, symbolized as F sub R, is calculated using the formula 1 divided by 2 times pi times the square root of the inductance L multiplied by the capacitance C practically. This means designing components for a specific resonant frequency, or tuning a variable component to reach that frequency. For example, in tuner circuits, you might vary a capacitor to select different resonant frequencies, effectively tuning into different radio stations. An important insight in parallel resonance is the concept of quality factor, or Q factor, which indicates the sharpness of the circuit's frequency response. A higher Q factor means the circuit is more selective, responding strongly only to frequencies very close to resonance. Also, while the source current is at its minimum at resonance, the currents flowing through the individual inductor and capacitor can be much larger than the source current, circulating energy between these two reactive components. This internal circulation current is often referred to as a tank circuit current. Understanding parallel resonance allows you to design highly selective filters, efficient oscillators, and precise frequency tuning circuits. By mastering how inductive and capacitive reactances precisely balance each other, you gain the power to harness alternating current behavior, making your electrical designs incredibly efficient and accurate for specific applications.